In this last video for Chapter 8, we talk about so-called improper integrals. They're called improper because the limits of integration involve infinity, or because if we plug one of the limits into the integrand, it makes the integrand infinity. We're mainly interested in this section in these two improper integrals. One to infinity of dx over x, and 1 to infinity of dx over x squared, or dx, actually anything with power higher than 1. This should be dx over x here. So let's take a picture to look at these two integrals. Remember, integral is the same as area, so both of these integrals are the area under the curves, this curve being 1 over x, this curve being 1 over x squared. So it's the area under these curves on the interval 1 infinity. So let's look at these two curves. So here we have the area under 1 over x, and here we have the area under y equals 1 over x squared. You can see easily see that this area here is much bigger than this area here. But let's find out the what this area is. We've got infinite regions. It should be the case that both areas are infinite. So let's do the first integral on the next blackboard. So we've got the integral between 1 and infinity of dx over x. That is what, ln of x, between 1 and infinity, and that's the same as what, ln of infinity minus ln of 1. Sometimes we would write this as a limit, as another way to write that would be ln of m as m goes to infinity, limit as m goes to infinity. But in either case, what we get here is that this is infinite. So this area right here is infinite. We have an infinite region, and we have an infinite area. Let's look at the next integral, though. So the next integral of the dx over 1 between 1 and infinity of dx over x to the minus 2 can be written like this, and that when we integrate it is minus 1 over x. Let's write this as a limit. So as a limit as m goes to infinity of minus 1 over x between 1 and m, which is the limit as m goes to infinity, minus 1 over m plus 1. But as m goes to infinity, this fraction just goes to 0, and so we get this result of 1, and so this area right here is finite. So we have an infinite region and an infinite area here, and an infinite region and a finite area here. Can we generalize this? Yes, we can, and let's do that on the next blackboard, following what's on page 187 in the textbook. So if we've got the integral between 1 and infinity of dx over x to the p, we already found out that it's infinite if p is 1, finite if p is 2. Let's integrate it in general, so it's 1 to infinity of x to the minus p dx, which integrates to x to the 1 minus p over 1 minus p, right? Because we add 1 to the power and then divide by that power between 1 and infinity. And that is going to be the limit as m goes to infinity. Let's divide it into two cases. So, case 1 will be when p is greater than 1. So if p is greater than 1, then this exponent right here is a negative number. So let's write this a little bit differently. So we've written this differently in the case when p is greater than 1 and in the case when p is less than 1. If p is greater than 1, then as we said, 1 minus p is negative, and so what we want to do is write 1 minus p like this. And when we write 1 minus p that way, then this exponent right here becomes, we can sort of treat it like a negative exponent and then move it to the denominator as p minus 1. And then this expression right here, the same thing, right? We're writing it as a negative of p minus 1. And so that's why we get p minus 1 here and the negative sign here. So let's clear all of those marks out and hope that that explains why we've written it in this p greater than 1 case here. We haven't we haven't done anything different with the second case. So let's look at this p greater than 1 case on the next slide, next blackboard. So p is greater than 1, we've written it this way, m is going to infinity, and so this expression right here goes to infinity, which means this whole fraction goes to 0. This fraction right here is just what? It should be another minus sign here. So this fraction right here is just 1 over p minus 1. So when p is greater than 1, this integral back here is finite, and it is 1 over p minus 1. Remember, we already did the case 1 to infinity of dx over x squared, and we got an answer 1, which is consistent with this general case answer. And then we look at the other case when p is less than 1. We've got what? P is less than 1, we've got the limit as m goes to infinity of we've got what we have here, but m is going to infinity, so this numerator is going to infinity, so this whole fraction goes to infinity, and so that's how we get the infinite case. So summarizing, we've got the integral 1 to infinity dx over x to the p has two possibilities. When p is greater than 1, it is finite and 1 over p minus 1, and when p is less than or equal to 1, we actually already did the less than case or the equal case way back here, right? This is the P equal 1 case right here. And we found out that it was infinite. And so, and we just did the P less than 1 case here. And so combining that together, we get this. So most of the examples in this section are just variations of this. The main result is this, and on the exam I'm going to want you to know how to verify these two results, the finite case that gives 1 over P minus 1 and the other two cases that give infinite. This P integral, as it's called, turns out to be extremely important in the next chapter to help us understand for infinite series which ones are going to have finite answers and which ones are going to have infinite answers. So this concludes this video on improper integrals and concludes the video set, or the set of videos for chapter 8.